This screencast is about checking the model assumption of independence. A check of the independence model assumption is required only when data is collected in a time sequence. For cross-sectional data, that is, data collected without a time component, the independence assumption is considered satisfied when the other three model assumptions, linearity, normality, and equivariance, are verified. For this section, we assume that bivariate data has been collected and collected in a time sequence, and that the data point index I reflects the time order of collection. Thus, the first data point x1, y1 was collected first, the second data point x2, y2 was collected second, and so forth. To check the independence model assumption, we first fit a simple linear regression model to the data and obtain the regression residuals. We refer to the regression residuals as E1, E2, etc. We then create a residual time series plot. That is, we create a scatter plot of the points 1, E1, 2, E2, etc. Here is an example of such a time series plot. A residual scatter plot showing random scatter, that is, no pattern, would favor concluding that the independence assumption is okay. A residual scatter plot showing random scatter, that is, no pattern, favors the conclusion that the independence assumption is okay. This scatter plot shows a definite cyclic pattern. The residuals tend to overcluster or change too slowly over time. This type of residual time series behavior is common and is referred to as positive autocorrelation. Positive autocorrelation suggests the independence model assumption is violated. In several pages, we'll introduce a hypothesis test for positive autocorrelation that uses the Durbin-Watson test statistic, D. Let's become familiar with this test statistic. D is computed as a quotient. The numerator is the difference in consecutive residual values, with those differences being squared, and then sum the overall differences. The denominator is SSE, the sum of squared residual values. D is always between 0 and 4. D near 0 indicates residuals are positively autocorrelated, as on our picture up here, where the residuals tend to overcluster. D near 2 indicates residuals are not autocorrelated. That's the preferable situation. D near 4 indicates residuals are negatively autocorrelated. That means the residuals tend to over-alternate. Up here, that would be going back and forth with every change in residual. This would be a pretty good time to stop the screencast. Try to guess the value of the Durbin-Watson statistic based on these interpretations for our residual scatter plot up here, which we've already discussed showed positive autocorrelation. Then move up here to this page and attempt this U-try. It's again pretty straightforward. It has you actually computing the value of a Durbin-Watson statistic and plotting the residual values. So I'll see you back here in a minute. The top of this next page indicates how to compute the value of the Durbin-Watson statistic in Excel. For this example, we'll assume n equals 100. Column A indicates the data point index, which is also assumed to be the time order the data was collected in. Column B indicates the regression residual values obtained from Excel simple linear regression output. Column C squares the residual values and adds them up to obtain SSE. Column D indicates the squares of the differences in consecutive residuals. Summing column D then gives the numerator of D. Thus, the value of the Durbin-Watson statistic is the quantity in D102, that's this quantity, the numerator, divided by the quantity in C102, and that's just SSE. When data is collected in a time sequence, the simple linear regression model assumption of independence must be evaluated. Two items are required. One, a time series plot of the regression residuals, and two, a 5-step hypothesis test for positive autocorrelation. The hypothesis test is needed due to the simple linear regression statistics we'll use later not being robust to the assumption of independence. All 5 steps of this hypothesis test are required when writing up the module homework. The first step in the hypothesis test for positive residual autocorrelation is to state the null and alternative hypothesis. The null hypothesis is the verbal statement, positive residual autocorrelation is not present. The alternative hypothesis is again a verbal statement, positive residual autocorrelation is present. There is no population parameter notation used in this hypothesis test. The second step is to choose a significance level. We place a maximum probability of alpha on incorrectly deciding that positive residual autocorrelation is present. The third step is to state the test statistic and its probability distribution. For the Durbin-Watson statistic, there is no additional model assumptions. The test statistic is D, the Durbin-Watson statistic, and D is distributed with the Durbin-Watson distribution with parameters K and N. In simple linear regression, K is always 1. The fourth step is to use Excel to compute the value of the Durbin-Watson statistic, as we did up here. And then we look up the lower critical value and the upper critical value in table E8 in our textbook. For those operating without a textbook, you could search critical values of the Durbin-Watson statistic and get a similar table. The fifth and final step is to make our decision. If the value of the Durbin-Watson statistic is less than or equal to the lower critical value, we reject H0 and decide that positive residual autocorrelation is present. That is, that the independence assumption is not satisfied. If the computed value of the Durbin-Watson statistic is greater than or equal to the upper critical value, we fail to reject H0. That is, we decide positive residual autocorrelation is not present. On the next 3 pages, there's an example where the data has been collected over a 24-month period. The data has a time component. With warehouse distribution cost as the dependent variable and the number of orders received during the month as the independent variable, a simple linear regression model is fit. The primary question in this example is, whether the simple linear regression model assumption of independence is satisfied. You should review this example.